Okay, so we're back. Sorry for the short one there. And what we're looking at here is, again, conditional probability. So under the condition that, and it's written like this. So what this would mean is, well, let's start off with this. Here's the formula for it. The probability of B given A is equal to the probability of A and B divided by the probability of A. So let's take a look at this as say, for example, cards. What's the probability of getting a queen, we'll go with a queen, given that the card is red? Now the formula is this. It says the probability of B given that A has happened is equal to the probability of A and B, meaning both events have happened, divided by the probability of A. Notice that this looks like a fraction and this is in the denominator. A is in the denominator. Okay? Now, since we're talking about one event, really what this A and B here is what meets both criteria. So if I were to write this as this would be equal to the probability of a card being both queen and red over the probability of that card being, and again, A looks like it's in the denominator, A goes here, red looks like it's in the denominator, red goes in the denominator, red. Alright, so probability of queen and red divided by the probability of red. So the probability that a card is both queen and red, there are 2 red queens out of 52 cards. Divide by probability of red. There are 26 out of 52 red cards. So now I've got 2 over 52 divided by 26 over 52. And dividing by a fraction is icky, so I multiply by the reciprocal. So this means I multiply by 52 over 26. And the 52's cancel, and you get an answer of 2 out of 26. And we leave it as 2 out of 26, not 1 out of 13, but 2 out of 26. Okay, but what does this really mean? Given that your card is red, meaning I know that the card is red. So what I'm going to do is I'm going to redefine the probability. Instead of being all cards, I'm limiting myself just to red cards. Just like when we said this, with a conditional distribution. Under the condition that you have survived. Meaning we are just looking at this group right here, just at the group that is alive. Same thing we're doing here, under the condition that your card is red, which means that my new population size is 26. So I'm going to replace this line with a fractional line, and I'm saying red cards, there are 26. Of these 26 cards, how many of them are queen? Of those red cards, how many of them are queen? 2. 2 out of 26. I've redefined the population to be 26. Of that, how many are queens? 2. 2 out of 26. 2 out of 26. A much easier way to do it. Now, does this mean that I'm not going to use at some point? Of course you're going to use at some point. It's a math class, for goodness sake. But here's an easy way to look at it. Okay, move it on over. Alright, when 2 events A and B are independent, we can use the multiplication rule, which we did before for independent events, and say the probability of event A happening and then the probability of event B happening is equal to the probability of A times the probability of B. However, what happens if our events are not independent of each other? Then what do? We're still going to multiply. But instead of multiplying by the probability of event B, what we're going to do is we're going to multiply by the probability of event B given that event A has happened already. And as we look at this, what it's saying, here's the probability of event A, and then we find the probability of event B. But it's really easy. What this is saying right here, in this phrase right here, probability of B given A, which is going to end up saying, oh, but that's confusing right now, is use your common sense. Realistically, use your common sense. So what does it mean in this context? What's the probability that I draw a king and then I draw a queen? That's what the question is asking. Probability of A and B, all right? So the probability of A and B is equal to the probability of A times the probability of B given that A has happened. Writing this out in that format would be the probability of king times the probability of drawing a queen given that you've drawn a king already. Use your common sense. All right, what's the probability of drawing a king? 4 out of 52. You've drawn a king. What's the probability that you are now going to draw a queen? Well, that would be 4 queens out of 51 cards. But this is something that you understand how to do. But it's written like this. So what you need to do is you need to take your knowledge of what you understand with common sense and say, oh, that's exactly what this means. So it means use your common sense. What's the probability of the second event in this situation? That's what it's saying. You're still going to multiply just like we did before, but has the probability changed? All right, now, we talked about independence before. And when we talked about independence, back when we were talking about distributions, we use conditional distributions to check for independence. And if we remember this, we would do something like, let me bring up, boy, I'm using this thing a lot. We would do something like this. Okay, here is the pie chart for people who died on the Titanic, and it might look something like this. And here's the pie chart for people who were alive on the Titanic, and it might look something like this. And we would say, okay, are those the same? If these pie charts, meaning the percents, are the same, then these two variables, alive and dead, and then the variable of class, that's broken down in here, would be independent of each other. Meaning there is not a relationship whether you survived or died or whether your class, one is not going to influence the other. And this is really how we defined independence before. Because when we were talking about independence before, and we were saying, okay, what does independence mean? Well, it means, does the first event influence the second event? If I roll this die and I roll a 6, the probability that I'm going to roll a 5 the next time is 1/6. And because those two probabilities are the same, therefore they are independent. But when you pull a deck of cards, the probability that you pull a king the first time is 4 out of 52. And the probability you pull a king the second time, regardless of what you got the first time, is going to change. We said that that means that those two events are not independent because the first card influences the second card. So here's the exact same thing. Now, let's look at this real quick. Again, because what we're going to say is that we can show independence by showing this statement right here. The probability of B given that A has happened has to be equal to the probability of B. Meaning, I look at the second event based off the first event, and that has to be equal to the probability that the second event happens all by itself. Let's take a look at it in these terms right here. Let's see if this is going to come up for us. It is. Okay, so let's go back to the probability of me getting a queen given that I drew a king. And the general formula here is the probability of B given A has to be equal to the probability of B. Okay? So, what this means here, the probability of queen given king would have to be equal to the probability of getting a queen all by itself. Alright, if that's the case, then these two events are going to be independent of each other. So the probability of drawing a queen, given that you've drawn a king, is going to be 4 out of 51. But the probability that you draw a queen all by itself is 4 out of 52. They are not the same. Therefore, they are not independent. And this is what you have to do. When it says, are these two events independent? You have to show it mathematically. We will do it in practice. Okay, independent versus disjoint. Again, we've got to be careful with this, okay? Really what we're talking about, are disjoints independent? And the answer is no, they can't. They can't be independent. Since we know that disjoint events have no common outcomes, no outcomes in common, knowing that one occurred means that the other didn't. So if we talk about rolling a 3 or a 4, if I got a 3, therefore I didn't roll a 4, therefore they're not going to be independent. Be careful with disjoint and independence. Oh, here we go. Coming back after the break.